Welcome everyone for joining us this evening here on our program with the virtual star party. Very nice, cool evening, great for doing observations. I'm Dr. Billy Teets, and I am the outreach astronomer here at Vanderbilt University's Dyer Observatory, and I'm also the acting director at the time. So tonight, as we go through our program, we're going to be checking out a lot of different objects that we haven't seen before, at least on this program. And as we're talking about these different things and discussing different concepts, please make sure to post questions into the YouTube chat. If I recall correctly, you have to be logged into YouTube to be able to chat, but I could be wrong on that. So, but please do post questions. Also, one thing we would also like to encourage you to do is post suggestions for different topics that you would like to see in future programs, or maybe some objects that you would like to see. We would love to hear from you all on that. So we've got another great program this evening. We've got presenters from here at Dyer Observatory, the Barnard Seaford Astronomical Society, the Memphis Astronomical Society, and Bays Mountain Park and Planetarium. But before we dive into it, I also want to give a big shout out to a few people that are working diligently behind the scenes to make sure everything is working out correctly. We've got Brian Smokler from VU News and Communications, and we've also got a couple of my colleagues here at Dyer Observatory, Mr. Nathan Griffin and Alex Rockefeller. So I want to thank all of them for all of their hard work, and all of our presenters for helping make this possible this evening. So let's go ahead and dive right on into it. So our first object of discussion for this evening is going to be the planet Saturn. So let me share my screen right quick. All righty, so now you all should be able to see Saturn. My presenters could give me a nod, yes or no, if we can see it. All right, thank you. So you can see Saturn is wobbling around just a little bit. It's not actually doing that. That's an effect of our atmosphere. And as the air above us is moving around, like tonight you can go out and you can feel a little bit of a breeze out there, but in the upper layers of the atmosphere and in all these different layers that have different temperatures and densities, all those layers are moving. And as the light from Saturn or the moon or the stars comes through those moving layers, it bounces around. And that's what causes our planets to kind of move around like this, causes the stars to twinkle. But as we say tonight, our seeing is pretty good. We can actually see quite a bit of detail in Saturn. So one thing I want to point out is that obviously Saturn has its magnificent ring system. You'll notice that the rings don't extend really visibly anyway in this view all the way down to the top of the atmosphere of Saturn. There are ring particles down in here, but they just aren't as visible in our view here. You'll notice that within the band of the rings, we see this very thin black line that's kind of going in and out. And so that black line is known as the Cassini division. And it's actually caused by a moon that's in orbit around Saturn. We'll talk about that in just a moment, and I'll show you what that moon actually is. So let me bring up the gain, kind of overexpose Saturn here. I want to get some faint objects visible. All right, so there we are. So now we have a couple of the moons here. In fact, let me zoom out just a bit. Right up here, this big bright moon, that is Titan, second largest moon in the solar system, largest moon of Saturn, only moon in the solar system to really have a substantial atmosphere. It's mostly nitrogen. Very cold on that moon. Several hundred degrees below 0 Fahrenheit. But you'll notice that around Saturn, we've got a few of the other moons, which are noticeably smaller than Titan. But on a good clear night, if you've got good dark skies, good seeing, and a decent sized telescope, you can actually pick out about 4 or 5 of these moons. And then when you look at them on consecutive nights, you'll see that they've actually moved quite a bit. So let me bring the exposure back down here. There's one other thing that I wanted to, oops, wrong button here. There's one other thing that I wanted to kind of point out. And if we zoom in on Saturn just a bit, you'll notice that its atmosphere is not perfectly uniform. There's a little bit of a banding to the atmosphere. And so if you remember when we looked at Jupiter in our previous star parties, we could really see a lot of features in the atmosphere of Jupiter. We can see some atmospheric features in Saturn as well. And a lot of those bands are really created by high winds on Saturn. In fact, Saturn's got some of the highest winds in the solar system, only surpassed by Neptune, as it turns out. But now let me switch over and do a quick little presentation just to show you some other things about Saturn. Just give me 1 second. Share. All right. Okay, so can everybody see the multiple views of Saturn now? Okay, thank you. All right, let me go back here. So this is, or these are, I should say, multiple views of Saturn taken over a number of years, actually about 11 years by an amateur astronomer. But what we see is that Saturn looks like it's changing its tilt. Now, Saturn is tilted over on its axis about like the Earth is tilted. It's actually just a bit more. But as a result of that, we see Saturn at these apparent different tilts as Saturn is orbiting around the sun. So every year as we take a look at Saturn, when it's nice and high in our evening sky, we see Saturn in a little bit different position in its orbit. But because it keeps that tilt in the same direction, we see it appear to change its tilt, but it's not actually changing its tilt. It's just our viewing perspective that's changing. One thing you'll notice is that when the rings go edge on, they are really, really thin. In fact, they're not perfectly edge on in this view. When the rings go perfectly edge on to us, for a couple days, about every 15 years, they are so thin that we cannot see them at all. Not even the most powerful telescopes in the world, not even the Hubble Space Telescope is able to pick out the rings. Because from one side to another, these rings are about 180,000 miles wide, but they're much less than a single mile thick. So if you wanted to make an actual scale model of the rings of Saturn by using a sheet of paper, your sheet of paper would actually have to be about as wide as 6 or 7 football fields. So they are super, super thin, but they're mostly ice particles. If you took all the rings and you basically smushed it together to form a single object, it would basically make an object about the size of one of Saturn's small icy moons. And in fact, it's thought that maybe these prominent rings were caused by a moon getting too close into Saturn, and Saturn's gravitational forces, what astronomers refer to as the tidal forces, basically ripped apart that moon to form these rings. So speaking about seasons and tilts, so if you have a tilt on your axis, then you'll have seasonal changes. That's what causes our seasons here on the Earth. It's not our distance from the sun, but it's actually the tilt on our axis. So our seasons are caused by the changing amount of daylight and how high and direct the sunlight actually comes in on the Earth as a result of our tilt. So you can see that the other planets, a lot of them have tilts very similar to the Earth. So Mars, Saturn, and Neptune all have similar tilts to us. Jupiter, it's almost straight up and down, so it really doesn't have much of a seasonal change. Venus is kind of basically upside down, which is why it has this super extreme tilt. But I bring this up because when we see, when we get a view of Saturn during its equinox, basically the sun is over its equator, we get a really neat view, especially if we have a probe in orbit around Saturn. So this was a view taken from the Cassini spacecraft several years ago. Cassini was actually deorbited into Saturn back in 2017. But there's a couple of things I want you to notice on this. So this picture is taken during the Saturn equinox. So just like here on Earth, when we have an equinox, the sun is directly over the equator of the Earth. So in this view, the sun is directly over Saturn's equator. And that's also where the rings orbit. Normally, we would see shadows of the rings on the planet, but this very, very thin strip right here, this very thin hairline band, that's actually the shadow of the rings, just to kind of give you an idea of how thin those rings are. The rings aren't nice and bright like we saw in the previous images because the sun is basically at the side of the rings. And so it's not above them to kind of shine down and illuminate them and make them appear very bright. But we see that the rings are illuminated a little bit, and that's because of reflected sunlight off of Saturn itself. So it's a really cool view. We can't get a view like this from the Earth because Saturn's orbiting out past Earth's orbit. So we don't get to see it in this nice, almost half, you want to say half moon phase, if you will. But it's a really cool view there. And then the rings, just to mention that they are not solid. They are made up of countless numbers of tiny particles ranging from dust grain size objects to basically boulders the size of a house. But they organize themselves into all these ringlets. So all of these rings are in orbit around Saturn. So this is a nice close-up view taken by the Cassini spacecraft. So the rings have kind of been compressed here to get them to fit on the screen. Now, that gap that I mentioned earlier, that here is that gap, the Cassini division. You'll notice it's not totally empty, it does have some material in it. But as I mentioned, that's actually caused by a moon. And this is the moon that's doing it. It's called Mimas. And if you're a Star Wars fan, the first thing you think about is the Death Star. Turns out George Lucas came out with the Death Star about 2 years before the first image of Mimas was ever taken. So he didn't get his idea from that. But this moon, it's actually orbiting around Saturn as well. Now, if you were inside of this Cassini division, the time that it took you to take 2 orbits around Saturn, Mimas would take exactly 1 orbit. So you would, as we say, be in a resonance with Mimas. So particles keep meeting up with Mimas in the same spots in their orbit. And as a result, Mimas's gravity kind of clears out that area. So some of these other divisions, like the Inca division, that's a result of a resonance with the moon as well. So we even see resonances like this in the asteroid belt. So I want to just finish by mentioning that we've got a conjunction coming up in December. So if you've seen Jupiter and Saturn in the night sky, in fact, you can go out, should still be up by 9 o'clock, but go out, you'll see Jupiter is a really bright object in the southwestern sky. Saturn's the bright object just to the left or the east of it. Watch them over the next couple of months, and on a week at a time, you'll see that they're getting closer and closer in our sky. They're not actually getting closer together, but from our viewpoint, they are. On December 21st, they will get so close to one another from our viewpoint here on the Earth that it will likely look like they form a single object. This is what we call a conjunction, when 2 objects get pretty close to one another in the sky. So this is about 5:15 in the evening on December 21st. Now, if you have a telescope, this is the view that you can get in the telescope. So for comparison, the separation between Jupiter and Saturn here is about 1/4, or actually about 1/5 of a full moon diameter. So it's a really, really tiny separation. So if you've got a telescope, you'd be able to see both of these planets and some of their moons, like the moons we have here for Jupiter and the moons we have here for Saturn. You'd be able to see all of those at the same time. By the next day or the day prior to this, they'll actually be separated by a little bit more, and it'll be difficult, if not impossible, to get them in the same view of the telescope. So be sure to put that on your calendar. Hope for clear weather. We'll probably be doing a live streaming view of it, so hopefully we'll have some good clear skies. But they actually get together in the sky about once every 20 years. But this conjunction happens to be a really, really close conjunction. Okay, it only gets this close about every 400 or so years. So that is all that I have for Saturn. Before we move on, let's see if we've got a couple of questions, which, by the way, as we go through our program, if you're joining us for the first time, we'll take a few questions in between presentations, and then we'll have a longer question answer session at the end. So question, do the objects that make Saturn's rings all orbit at the same speed? And the answer is no. So Johannes Kepler, back in the 1600s, I think it was the 1600s, can't remember, it was late 1500s, early 1600s, came up with his 3 laws of planetary motion. Basically, if you've got an object orbiting, say, a planet, the closer it is to the planet, the faster it has to go around the planet. So all of those individual ringlets, they're all orbiting Saturn at different speeds. So the closer they are in to Saturn, the faster that they're going to orbit Saturn. And then the farther out they are, the slower they're going to orbit. Okay. All right, I have probably gone over my time there. So give me 1 second. All righty. So now we are going to head over to Goodlettsville, and we're going to visit with Thea Wellington. She's a member of the Barnard Seaford Astronomical Society. She's also a NASA Solar System JPL, or excuse me, a NASA JPL Solar System Ambassador. She's got a really nice telescope out tonight looking at a galaxy that we often refer to as M31. So I'm going to turn it over to Theo.
And is it possible that somebody else could step in first? I'm really, really close, but I haven't quite got it into the camera yet.
Adam, would you like to go ahead and move up?
Is that okay?
Yeah.
Or
I was going to see what Theo's saying.
is that okay?
Is that okay
Theo,
for you,
you
Adam?
want me to go?
Yeah, would you be able to go now? Are you ready to go?
I'm ready.
Okay.
Yeah.
So slight change of plans. We're actually going to go over to East Tennessee and visit with Adam fans of the Bays Mountain Park and Planetarium. So Adam's been into astronomy since he was 12 years old, and he received a master's degree in astronomy and education at the University of Florida. And he's been at Bays Mountain since 1992 doing lots and lots of education. So we're going to turn it over to Adam and check out a really cool cluster tonight.
Thank you. Yeah, do a little switcheroo here with our scheduling, but that's okay. So I've got an interesting double object, which is called the double cluster. As you can guess by the name, it is a double cluster. It's two open clusters of stars that are seen very close to each other in the night sky, and they are physically near each other as well. They're, close enough. So it's an interesting feature. So what I'm going to be doing here, I have a number of ways of showing this. First of all, I'm going to show you what my camera is getting right now. As you can see, it's not showing a whole lot of stars. And that's mainly because my camera can't get super duper faint objects in a live setting. Let me show you this picture for just a quick moment. Where is the double cluster in the sky? So here you should be seeing two constellations that I've highlighted. Notice the northeast direction. This is tonight, and you'll see it like this for the next month or so. But as the months go on, the difference will be is that these objects will be seen higher and higher in the sky as they arc across the sky, and eventually you'll see them in the northwest sky about 4 to 5 months from now. The double cluster is in between two constellations, Cassiopeia and Perseus. Cassiopeia is known as Queen Cassiopeia, and there's a whole story that goes along with Cassiopeia, as well as Perseus and Andromeda and Pegasus and Cetus. There's a lot there. And also includes Medusa. So please look that story up. We don't have enough time for the story right now, but the W shape of Cassiopeia is very recognizable. And there's actually one extra star that can be used to kind of create her throne seen upside down. And so she's actually sitting upside down in the throne, which is part of her punishment because of how vain she was. Below it, Perseus. He is the one that was the victor of the Queen of the Gorgons, Medusa. And if I'm going to give you a little pause here as to what was so famous about Medusa, a couple of things. One has to do with what was part of her makeup, so to speak. What was on top of her head? Snakes for hair. Pretty bad. The other was that if anybody saw her, or if she was able to look at you and you saw her, you would instantly turn into, another dramatic pause here, into stone. So I was trying to see if you could remember before I said it. So you would turn into stone. Perseus vanquished the Queen Gorgon of the Gorgons, Medusa, by not looking at her, but at her reflection in his shield, and was able to vanquish her. And so that's part of the storyline. Right in between those two constellations, though, you see that little square. Okay, I'm behind the logo on YouTube, but that's okay. The square is highlighting where the double cluster is. It is visible to the unaided eye, just in the night sky if you have a dark sky. Binoculars, though, will show it in most any sky as long as it's clear. So binoculars in between the W of Cassiopeia and kind of the double hook shape of Perseus. And you'll see these two fuzzy spots. All right, so next picture. This picture I took about 5-10 minutes ago, and it wasn't a very long exposure, only a couple seconds, but it was just the difference between me being able to show you a live image and a captured image. There you can easily see the two clusters. An open cluster can be found in the plane of our galaxy. So Theo, hopefully things will work out for her. She's going to be showing you a spiral galaxy, a spiral armed galaxy called the Andromeda Galaxy. And you're going to see these big spiral disk shape to it, kind of like a pancake in space with a central bulge. And open clusters are found in that disk. And so that's what we don't typically find them high away from the disk of the galaxy. They're kind of along the disk of our galaxies that we find them. And these two clusters are visible. And in fact, let me show you, tell you a little bit about it. So they're along the Milky Way. They're also known as H and Chi Persei because they're officially in the region of Perseus. They're both around 4.3, 4.4 magnitude. And so it's not the limit of your vision at night for really dark skies is about 6.5 magnitude. 4.3, modestly dark skies, you'd be able to just spot it. They're about 30 arc minutes wide, so half a degree. It's about the same visual size as the moon and the sun. There are about 350 total stars in these two clusters, about 7,000 light years away, and easy in binoculars. Now, I mentioned the term light years. Well, a light year is the distance light travels in a year. It's at 6 trillion miles. That's a 6 with 12 zeros after it. And so it's 7,000 of those away. So it takes 7,000 years for the light from that cluster, those two clusters, to reach us. Let's see here. Okay, I'm going to show you one more picture. This is a photograph I took about 3 to 4 days ago. And obviously a little bit longer exposure. A lot more stars can be seen. And you can really see the cluster pattern itself very easily. But also it's in the Milky Way. So the sky, that whole picture is just filled with stars. Just to give you an idea about how large of a part of the sky that is, it's got top and bottom is a little over 2 degrees of sky, left and right, a little over 3 degrees of sky. So that's a lot of sky. It's a very low magnification image, but you can just see how nice the clusters are and how rich that star field is. Again, find them between Cassiopeia and Perseus. Look with binoculars. And that's now in the northeast. You see that it's about 30 degrees up off the horizon right now after sunset when it gets dark. So do try for that. Let me bring my picture back up. And let's see, I see some questions. Okay, how many galaxies do we think there are? A lot. Actually, Theo's going to be talking about galaxies, but we don't know the true number. But to quote Carl Sagan, in the way he would say it, billions and billions. There's just, we don't know how many there really are. There's just so many. And each galaxy has typically billions of stars. There are more stars out there than there are grains of sand on the entire Earth. And so that kind of gives you an idea about, right, I know it kind of blows your mind. If you ever watched Cosmos with Carl Sagan long ago, that's where that came from. And is there a name for the double cluster? The double cluster. That's truly, that is the name, the double cluster. And just to look at my notes, just to make sure, they are also known as H Persei and Chi Persei. And if you want to get detail, there's the new general catalog numbers of 869 and 884. Not as exciting as the double cluster, which is exactly how it looks. I'm going to stop right now and I guess give it back to Billy and then Theo. Thank you.
All right, well, thank you very much, Adam. Theo, are you squared away over there? I think you're still muted. There we go.
Yes, we are good to go.
All righty. So let's go back up to Goodlettsville in northern Davidson County to Theo Wellington, who I mentioned before is a member of the BSAS, the Barnard Seaford Astronomical Society, as well as a NASA JPL Solar System Ambassador. And she's going to be talking to us about a galaxy tonight and also showing it to us. So Theo?
So yay. Yeah, this is one of our showpiece objects, although it is and it isn't, for reasons that we're going to make clear. It's, I think, one of the coolest things you can look at. But let's see, I'm going to start a couple of slides here and then share that screen. So from current slide. And sugar, I need to. Okay. Get that down. Hang on. Okay, escape from that. I need to haul this over to here. Here we go. Now I can start that from current slide. There we go. And share screen. Does anybody else talk to themselves when they do this stuff? Okay. Share. Let's see if that works. Not that one. That's not who I want, actually. Stop. That's not who I want to share. I want to share this guy. And that slide. All right, we're kind of in the same area of sky as Adam was in, just a little moved over. Kill that, so that goes away. And that's screen sharing, but it's not showing the slideshow, is it? Let's do this. There we go. So in tonight's night sky, what I would look for is Mars, just because it's big, it's bright, it's stupid easy to find. And so there it is, circled in our eastern sky. And then, like he was talking about, there's a really prominent W of Cassiopeia. If you can see a queen sitting in her chair in that, you're doing really well. I just see it as a 3, a W. You know, again, your imagination is your own. And then that great big square. And again, there's lots of shapes you could make of with that. And every now and then I'd get a really pedantic teacher in the planetarium that would say that's not quite a square, but we call it the Great Square. And then I like to hop down 1, 2 kind of bright stars from that corner of the square. And this works stupid well with binoculars, by the way. And then you hop up 2 not really bright stars, but in binoculars, they stand out really well. And you will not be able to help yourself. You're going to run across, and I was using the binoculars just a few minutes ago, actually, to help me point the telescope. You'll run across this fuzzy thing that looks like somebody stuck a piece of cotton ball up there in the sky. And when you really zoom in, you know, in pictures, it looks super cool. This is the kind of picture you often see on the back of a telescope box to try to sell you the telescope. And people will, you know, then ask us, why can't I see that? And the reason is your eye can't soak up light the way a camera does. That's a camera's view. What we actually see, and you can see this with just your eyes, especially here in the fall as it moves high, you know, by 10:30, 11 o'clock at night, it's pretty high up in the sky where it's a little bit darker. You can find this doing that star hop with just your eyes. Although if you try it first with binoculars, you'll find it, and then you can find it with your eyes. But what we see with our eyes is just that bright central core. We don't see that whole extended piece. Now, if we could see that central core, it'd be stupid cool, because that is actually over 2 times the width of the moon in the sky. So for example, here's the full moon rising over Nashville. Imagine if we could see that. That would be super cool. So Andromeda, it's a huge galaxy, okay? Much like our own Milky Way. So, and we're neighbors. That's our nearest large neighbor galaxy in space. Oh, we keep going back and forth about who's got more stars or who's got more mass, but we're both really big. We are members of what astronomers call our local group. It's our neighborhood of galaxies. Now, astronomers have weird ideas about what a neighborhood means. So it's over 2.5 million light years away. So the light that you can see, and to me, this is what makes it cool, even when it's just a fuzzy dot. The light that you're seeing hitting your eyes when you look at it with just your eye, or even through a telescope eyepiece, has been traveling since our ancestors were walking around Africa. And I just find that to be super cool. You know, the light's taken all that time to get here, and now it's finally here in your eye and you can see it. So roughly 1.2 billion solar masses of stars and stuff, maybe 1 trillion stars, okay? And it's a big galaxy, we're a big galaxy, and so we are actually coming toward each other. And wait for it, you know, in a couple billion years, the view is going to be amazing. So let me see if I can turn that off and move instead to the actual camera view, which I think approximates pretty well what you can see. I'll move this over here. If you had your telescope out, I'm going to share the screen now for the, here we go, fire capture, share. All right. Can everybody see that? Because I can't see if I'm sharing. So that big, long, extended, fuzzy thing is what, after an hour of nice long exposure, turns into that beautiful, beautiful galaxy. So it's kind of fun that, yeah, we just can't see it with our eye, but it's still a very, very cool thing to look at in the night sky. So it's both a showpiece object, right? It's this huge, really cool spiral galaxy, and it's something that people go, but all I see is this little fuzzy patch. Yep, that's all you see. But it's cool when you know what it is. And this galaxy, you know, we used to have these huge discussions about, were these nebulas that, because the first telescopes could only see it like this too. So was that outside? Was our Milky Way galaxy the entire universe, and these things were just fuzzy bits inside it? Or were they more distant? And this wasn't settled until early in the last century, when Edwin Hubble took a picture, or actually several pictures, and found a variable star that's in the Andromeda galaxy, and he could see that star's light waxing and waning in a regular manner. And those particular stars do that in a way that how long they take to wax and wane is related to their brightness. And we can find those stars really close to us and measure their brightness, measure their distance with just trigonometry. So then we can use their brightness when we can't measure them that way to make a distance scale. And what he found was that this was, you know, hugely further out. All of a sudden our universe was huge. This was obviously outside the Milky Way and an island universe all unto itself. So that's what makes it stupid cool. And yeah, it's our nearest galaxy in the neighborhood, so we can wave, hi neighbor. And it probably has a nice big black hole in the middle of it, just like we do as well. So does anybody have any questions? And somebody would have to relay those to me, I think, because I don't have the Zoom or the chat open at the moment.
Thank you, Theo. So are M110 and M32 gravitationally bound to M31?
Yes, those two little satellite galaxies. And they are much like our own Magellanic Clouds. So, yep, they are going around it. And yeah, gravity is fun, and it works even on these incredibly huge distances. So someday there will be a collision, and there will be a much larger elliptical galaxy out of all that. And people have dubbed that Milko Media, which is kind of silly, but long before that, maybe in 1 billion years, 2 billion years, the view is just going to get awesome as this thing gets closer and bigger and brighter in our sky. All right, anything else?
I think that is it for now, but we may get some more questions here in a little bit.
All right.
Thank you so much, Theo. That was really cool. So now we're actually going to go over to West Tennessee and visit with Jeremy Veldman, who is the president of the Memphis Astronomical Society. He's actually observing from the Sky Shed, which is the backyard observatory of Merrill Miller, who is another member of the Memphis Astronomical Society. And so tonight, Jeremy's going to be showing us a few deep sky objects, namely a galaxy and a type of nebula. So I'll turn it over to Jeremy.
Thank you very much, Billy. First of all, quick sound check. Give me the thumbs up if I'm all right. Excellent. Yeah, so doing something a little different tonight. I'm actually at my buddy Merrill's house. Merrill is a new member of the Memphis Astronomical Society, but he's been in the astrophotography space for years. And he's a retired engineer from Procter & Gamble, worked in Jackson, Tennessee for a good period of his career. In fact, if you like the snack food Pringles, at one point in time, he worked at the plant there and was, among other things, the world's largest distributor of the snack food Pringles. I find them highly addictive. You can't eat one or two. I usually can down a can pretty easily. So just a little fun fact there. But let me go ahead and share my screen and give you a better idea of where we are. So I'm gonna go ahead and start from the beginning here. So can everybody see that all right? Hopefully you can see the presentation. Hang on 1 second. Let me stop the share because what it's doing is it's putting the PowerPoint presentation. Let me do this from the beginning, and then I will, oh, okay. That's a second here. Let me end the show. All right, what I'm gonna do is, I don't know if you guys can see this. I'm gonna go ahead and share the screen again, and I'll just walk through the presentation. Oh, here we go. Let me do that. So can you guys see that all right? Yep. Okay. All right. So this is the backyard of Merrill Miller's house, and this is where we are tonight. And you can see here the view of the Sky Shed. When he built his house in 2011, he actually laid the foundation for this Sky Shed. And of course, you know you've arrived in the world of astronomy when you have a backyard shed with a dome on it. And inside the dome is this telescope right here. This is a 14-inch Meade, and it has an S-big camera with adaptive optics connected to it. And it's on an AP 1100M mount. So this is his rig for astrophotography, and it is completely automated. So he not only has the hardware in place, but all the software in place for doing imaging, and it's completely automated. It's run by software. So he can literally set it up, run it, go to bed, and it will just image and gather data throughout the course of the night. And then he does all his post-processing after the fact. So, and then of course, here's where he controls it. This is where I am tonight. This is the actual control center. So, and we'll just kind of show you a few things here for what he does. Now, the first image we're going to look at, the first target is the Pinwheel Galaxy. And this is Messier object M101. Now, this is a face-on spiral galaxy. You just saw the Andromeda Galaxy. It's the closest major galaxy to the Milky Way. So we can see it relatively easily. In fact, it's naked eye visible from a dark sky site. Pinwheel Galaxy, not so much. Because it's a face-on spiral, the surface brightness is much lower. So it's a really tough object to see. You have to be in really dark skies, big mirror to see it. And even then it's a fuzzy patch. but it's an excellent astrophotography target. Now, a little fact here about this galaxy. In 2011, a Type 1a supernova was discovered in this galaxy. And a Type 1a occurs when a dense nugget called a white dwarf accretes matter from a nearby companion, in this case, a red giant. And when it accretes enough mass, it will undergo a thermonuclear runaway and detonate. And when that happens, for a brief moment, it outshines all of the stars in its galaxy. Type 1As are pretty rare. This is the closest Type 1a supernova ever discovered. It was only 21 million light years away. Now, that's inconceivably far away for some of the objects that we look at in our own Milky Way, but for galaxies, it's still relatively nearby. The significance of this discovery is that Type 1a supernovas are a type of standard candle. And in the world of astronomy, they can be used to measure the expansion history of the universe. And this work was done in 1998, in the 1990s. And in 1998, it was the breakthrough discovery of all the sciences that year. And in fact, in the year 2011, these three men right here won the Nobel Prize. This is Saul Perlmutter, Adam Rees, and Brian Schmidt. We just talked about the Andromeda Galaxy colliding with the Milky Way. It turns out that's not how the universe behaves on large scales. The universe is not only expanding, it's accelerating, it's speeding up, completely counterintuitive. So Type 1As are very important objects. So now it's located, let me show you where it's located. If you can find the Big Dipper and the handle of the Big Dipper, it's actually right off the handle. So if you just draw an isosceles triangle, then that's where you find M101. It's, yeah, I guess an isosceles or an equilateral triangle. It's at the apex of that triangle. So it's a relatively easy target to find if you can find the Big Dipper. So I'm gonna go ahead and stop sharing the PowerPoint here. And I'm gonna go ahead and share now my general screen so I can show you the program. So hang on. New share. Let me do, okay, let me see if I can go to just a regular screen. Actually, let me go ahead and get out of this. Stop share. And then I'm going to go ahead and exit this. Hang on just a second here. All right, now I'll do a new share. Bring up the screen. Okay. So hopefully everybody can see this. This is TeamViewer, and this is the program.
TeamViewer is just the view.
That's the view, sorry.
Maximum
Okay.
DL.
Maximum DL is the program that actually runs the observatory. I'm just going to walk you through a couple of general steps. There's a lot of variables here in the process. You got the first step in the process is to find a focused star, because when you're doing astro imaging, you want to make sure that the telescope can track that object, because you're going to be taking longer exposures and then stacking them later. So the first step is to find a focused star, do the initial focus and calibration, and that's what's done here in the SBAG AO control window. Once that's done, then you're essentially set to do your plate solving, and then you can start doing your imaging. I'm not going to do that for M101. I'll show you a little bit about how the process works when we go to the second object, which is the Cocoon Nebula. But we took a couple of subs a little earlier of the of M101, the Pinwheel Galaxy, and I just want to show you what those look like. So typically in the world of astrophotography, you want to be doing at least 5-minute, what are called subs. And a sub is just like one exposure or one image. So if you set your telescope, and assuming everything is calibrated right and it's tracking, you get a 5-minute exposure. You do multiple exposures, sometimes for several hours, sometimes even several days. And then you do the post-stacking later. We're only going to show you the luminance data tonight. So in other words, there's several different types of exposures you take, which is the luminance data, but then you may go back and do something like hydrogen alpha and other filters, RGB. So this is the RGB data. So here's what whoops, that's we'll get that in just a second. Here's what a 5-minute exposure of the Pinwheel Galaxy looks like. Now in a telescope, you would see a fuzzy patch. Here you can start to see a little bit of structure. You can see the bright nucleus, which is typically what you see with a galaxy. And the nice thing about an astrophotography target is you can actually start to see some of the arm structure coming out from the pinwheel galaxy. Now here's a 12-hour integrated exposure. So in other words, 12 hours worth of data. Each one of these subs is 5 minutes long, and then you stack them. So you can see here a lot more detail coming out, including the bright nucleus. I mean, at the center of this galaxy, if you were on a planet orbiting a star near the center of this galaxy, it would be so bright that you would literally, it would be like daylight 24 hours a day. That's how dense the star is near the nucleus of this galaxy. So this is what a 12 hours worth of data looks like. And then the final image is, this is actually several hours and several days, and then also all the data stacked together. And here you can really see the richness of this target. So the full arm structure, and then of course, the one thing that's really fascinating about spiral galaxies is you get that density wave that propagates through the stars. And in the arm, you know, the arm structure is where the arms of the galaxy is where all the action occurs. That's where the H2 regions tend to condense and form stars. And that's what you're really seeing here is the brighter O and B type stars that, which is where most of the light from a spiral galaxy occurs. So that's M101. Now the second target, and let me go ahead and get back to my PowerPoint here. So I'm going to go in the screen share one last time. Let me bring up my PowerPoint here. Hang on. Okay. So hopefully I can get this here. Nope. Exit. Bear with me 1 second here. I want to show you the cocoon from current. All right, here we go. Now let me see if I can share. See if you guys can see that. There we go. All right. So the second object is the Cocoon Nebula. Now, Meryl's been working on this one for a little while. Similar to what we saw last time with the Trifid Nebula, this is a stellar nursery where new stars are forming. And it's an emission nebula. And again, an emission nebula occurs when you have excited ionized hydrogen gas. And then when the electron jumps from the third energy level to the second energy level, it emits this red light. So that's where you get this characteristic pink and reddish color. And in this case, the star at the center of this nebula is BD 463474 that's actually causing this phenomenon to occur. It's a very, very hot B-type star, 30,000 degrees. So let me go ahead and get back to the software here. And go ahead and get out of that and show you what this, okay, so we're gonna go back to our program here. I'm gonna actually show you the process of the telescope slewing to the target. There you go. All right, so everything is set up. We've done our focus star. We've done our plate solving. So now all I gotta do, and everything is already lined up here in the program. CCD Commander is the program that Meryl uses to do his astro imaging. So if I hit the play button, here's the actual process of the telescope slewing to the target. Is it slewing?
Yeah, there it goes.
There it goes. All right, so it's moving. You can see the telescope moving, and then the dome, the slit of the dome is open, and it's moving. Okay, there goes the dome. It's actually moving. So it's going to find the Cocoon Nebula, which is the second image or the second target that we're looking at tonight. And there you can see it actually moving to the target. And then we'll go back to our program. And again, we've got maximum DL working.
It's working now. It's running.
And you can actually see it running, right?
It's doing a plate solve.
So it's doing the plate solve right now. And now we are ready to start imaging.
Yeah, X that one out.
Which one? This one?
No.
This one?
A bit out.
All right, so X that one out.
See, it found the guide star.
So it found the guide star, and now it's actually in the process of imaging it, correct?
Well, as soon as it starts tracking.
Oh, as soon as it starts tracking. So here's the window that we're going to be looking at to see it actually start tracking, correct?
Yep. Just a second.
All right. Oh, there it is.
There it is.
There's our guide star. So now we just go to track, and now it's actually tracking.
It's running.
So that's it. So now he can actually image. Now he can just go to bed, and the process will be automatic because it's already set up. And every once in a while, he'll get up in the middle of the night and just make sure that this star is actually in the middle of the window. And he'll take what? Several hours worth of data throughout the course of the night and then stack them later. So that's pretty much it. So
Show the Pix Insight.
Pix Insight. Oh yeah, the Pix Insight. So let's look at the actual finished product. Here's a 5-minute, again, sub of the Cocoon Nebula. And here again, you can see some of the structure here, the emission part of the nebula, and these dark lanes right here, that's the dark part of the nebula. So regions of dust within the nebula itself that are obscuring light from coming through. So that's a 5-minute exposure. And then here is a 7-hour exposure, quite a bit more detail that you can actually see in here. And you can notice the stars are nice and round and crisp, meaning the calibration was set up correctly. And then the final finished product here is one that he worked on. And this is a really beautiful image.
Years ago.
So again, you can see the luminance, the full color, mostly the red again, because of the hydrogen alpha emission. You can also see some of the blue, which is indicative of oxygen. And then of course the dark lanes right here, which is a dark nebula. So it's really a combination of emission, dark, and reflection nebula. So this is the Cocoon Nebula final product, several hours worth of data, and then also stacking. So that's pretty much it. We'll go ahead and stop share now and see if anybody has any questions.
So we did have a couple of questions. One of them was, so if you go back to the really nice image of the pinwheel, why did the two stars have rays coming out of
Just for looks.
Let me see, where is that? Is that the final one?
They're called refraction spikes.
Oh, okay. Yeah, those are refraction spikes from the stars. That's all that is. Yeah, that's just for looks. That's all that is. That's not it's not actual any natural phenomenon, just an imaging phenomenon.
Let's see, and there was one other question. This one might be more for the end, but where are we likely to find habitable planets? So think, anybody
Yeah.
here that, please.
You don't want to, yeah, that's an interesting question. So the general principle in a spiral galaxy, first you want to be, you don't want to be too close to the center of the galaxy, because that's typically where the O and B type stars are located, and they just spew off massive amounts of radiation, which would probably obliterate any life if it was getting started on a world. You don't want to be too far out either, because you want to be in the galactic habitable zone, where you have stars that aren't going to kill you, but also enough richness of elements so that you can form structure, specifically metals. So just like there's a habitable zone around stars, there's also a galactic habitable zone where you're more likely to find stars that have the potential for Earth-like planets. So, K, G, and G type stars are probably your best bet.
Okay. Oh, and I had one question. So you had mentioned plate solving. Could you explain what plate solving means?
I'm going to defer to my man Merrill.
Well, somebody over time has created a catalog where the exact RA and deck of all the stars are, and you take an image and you just compare that to that catalog. And once they're exact matches, you know exactly where you're pointing. Because that's what's very important in a telescope, probably as important as anything, is that you can point to where you want to point.
Mm-hmm. So basically what you're doing is you'll take your first image through your telescope. The computer will then try to match that to an area that's around where you're supposed to be and say, oh, we're actually looking at this little section based on where I see stars that match up perfectly with these stars. So maybe I need to move the telescope down just a touch.
Well, what the process is, once you know where you are, you just sync the telescope to that location.
Mm-hmm.
So it's precise. So you can point anywhere else in the sky and you'll be where you want to be.
But then the plate solving basically allows the telescope to say, okay, I know exactly where I'm pointing now.
Correct.
If I need to move a little bit, now I know where I'm going to have to move to.
That's correct.
Okay. All right. Let's see. There was one other here. What bortle zone is Merrill in, and does he find himself having to use DVE and Pix Insight?
What Bortle sky? I think we're Bortle. Is it three? Three.
Three, probably. You know, if you look at the,
I guess it's a green zone. We're in a
no,
green.
I think it's yellow.
Oh, yellow
I think
zone.
it's yellow.
We're in a yellow zone.
Could you explain a little bit what
DBE, I'm sorry.
could you explain just a little bit what's meant by Bortle zone?
I believe gray is the best. I've got to refresh my memory on this. And then there's blue, and then I think there's green or yellow, and then green. So yellow is like third or fourth best. So you still, dark enough where you can see the Milky Way, but you still get some light domes on the horizon. I've got to brush up on the Bortle scale too. So if somebody else knows more, feel free to pipe in. But yeah, I think we're yellow. We're certainly not Bortle 1 or 2. I think we're probably 4 right here. So yeah,
Basically referring to how bright the sky is, correct? So
Correct.
if we're in like a gray area then, or a very dark blue area, then you would be in essentially very, very dark skies. But around a city, the Bortle map would look very orangey red because there's so many lights in the city, making it very hard to see, right?
exactly. We're in a yellow zone just outside of the metro area of Memphis. So
Gotcha.
Did I hear somebody ask about the DBE at Fix That Insight?
Yes.
What was the question about it?
So let's see. Does Merrill find himself having to use DBE in Pix Insight?
On all images, yes.
yeah, on all images.
You want to give a little info as to what that is?
It's dynamic background equalization, I believe, is the DBE, and it just basically flattens the background and makes it smooth. Because it's just a tool in Pix Insight.
Okay. All right. Well, I think that is all the questions we have at the moment. So with that, anything else, Jeremy, before we move on?
That'll do it. Appreciate it.
Thank you very much.
Thanks.
All righty. So now we are going to head back over to Middle Tennessee. We're actually going to be just a little bit southeast of Nashville, near Murfreesboro. We're going to join John Kramer, who's in Christiana, Tennessee. John is also a member of the Barnard Seaford Astronomical Society, and he enjoys sharing his love of the night sky live by broadcasting to sites such as the Night Skies Network, and he's even got his own YouTube channel called At the Eyepiece. So I'd recommend that you all go check out his YouTube channel. It's a lot of great info on there. So he's going to talk to us about another galaxy tonight. So John?
Well, hello there, everyone. Give me a quick thumbs up if my audio is good, please, if the group doesn't mind. Awesome. Thank you very much. So, yes, I am broadcasting right from my little backyard observatory. Got the telescope about 15 feet or so away. And tonight you've been seeing some different galaxies, and that's cool because galaxies are awesome, right? I love galaxies, and they're really fascinating to go ahead and show. And the one that I've got lined up for you here is Messier 33, M33. Now, there's some really cool things about this galaxy, but before I start talking about it, well, let's go ahead and take a peek at the galaxy itself. So here is our live view. Well, I say live. Now, remember, Merrill, God bless him, 18 hours of integration on a particular object. I don't have that type of patience. But this is 18 minutes of 1 minute exposures, and it's stacked, and that's how we're able to go ahead and see this beautiful spiral galaxy again, M33. Now we're able to go ahead and pick out some of the spiral structure. Let me just go ahead and use, you can see here some of the arms spiraling out and some of the other ones here, maybe another area here. So that's why it's a spiral. It's almost face on. I don't believe it's a full face on galaxy, meaning completely perpendicular to us, but we're able to pick up that spiral structure fairly quickly in the telescopic view here tonight. So I'm very, very thankful for that. And if you were going to go ahead outside, keep in mind that this is a galaxy. They're generally well, they're dim, but in the realm of galaxies, this one actually is rather bright. This is just a little bit fainter than the galaxy that Theo was showing earlier, M31, and it's actually in the same group. We call it, I believe it's the local group of galaxies, and that just means that they're within our local neighborhood. You know, you got you got the Milky Way galaxy, which is of course our galaxy, and then you have M31, and then you have here M33. So a couple of interesting facts about M33 here is that, you know, I said it's bright, relatively bright for a galaxy, but it's still very challenging for you to see. You have to go ahead and be outside in a very dark sky site with exceptionally good clarity for that evening. And you have to have some pretty darn good eyesight in order to be able to nab M33 for yourself. But if you were able to do that, one of the cool things is you would be seeing the furthest object that you can see from Earth with M33 without using optical aid. So how cool is that? So that's kind of a challenge to throw out there for folks to spot not only the M31 that we were showing earlier, but hey, why not go for M33 if you have a pretty good sky in order to do that. So let's go ahead and flip our view over to Stellarium. This is a free product that I highly recommend. It's a planetarium program. It shows us where we are in the night sky, etc. So I am going to go ahead and try to help you all locate M33 for yourself. So you can see we're pointed just about here. So if we were to go outside and if you were to look towards your east, you would go ahead and see not only Mars, which is right here, but you would start to pick up the large square of Pegasus here, pretty prominent. Now, to locate our M33, you're going to have to follow a few stars and find a little bit of a dimmer constellation. So let me zoom in here just a bit. And I would say first start off at the tip star here on the corner of the large square of Pegasus called Alpheratz, and then kind of hop down towards Mirac. And from here, look lower towards the east, and you should be able to see a very dim constellation called Triangulum. And that, by the way, M33 is actually called the Triangulum Galaxy. Interestingly enough as well, you just had, I think we were showing a previous galaxy, the Pinwheel. Sometimes those get actually confusing. So for the purpose of tonight, I'm just going to refer to this as M33 because it's actually sometimes references the Pinwheel as well. But if you were to find, Mirac right here, and then the tip of the point of the Triangulum constellation here, that tip star is called Moth Allah. And I would say about 1/3 of the distance north of that, you might be able to spot M33. That's where we are looking. So a couple of other interesting points here on M33. Let's go back to our live view because, hey, you know, that's the cool part. I am not stacking at the moment, but that's why those messages keep popping up. But we have 18 stacks so far. We can do here. This is live. I'll take a chance. Remember the beautiful view that we have here because we're doing this live. So if something happens, well, it might mess it up, but we'll leave it going as is right here with M33. So a couple of other interesting points about it. It was one of the first objects that the Earl of Rose defined as a spiral nebula. You know, they didn't even know these things were galaxies. But also Hubble, that dude, Edwin Hubble, studied Cepheid variable stars in M33 to go ahead and determine that these things were not in our own galaxy. They were completely separate galaxies themselves. So I thought that was a really interesting point. And, you know, Charles Messier, he's the gentleman that created all of these objects, well, not all of these objects, but created a very cool list that as amateur astronomers we go through. He first added this object to his list back in 1764. So very, very cool there. Now, as we go ahead and we view this particular object, just because of the nature of M33, we kind of pointed out the spiral arms there. Hopefully this is coming through okay. All right, but one of the things here, so I can pick out a really nice spiral arm here. As we go through the core, we have another nice one here, but right at the end of that spiral is another really cool feature, not a very prominent feature of M33. It's a hydrogen 2 region. In fact, it's one of the largest hydrogen 2 regions in a galaxy itself. And if you had a large enough telescope and you were outside visually trying to scrutinize this object yourself at the eyepiece, you might be able to just pick up the fuzzy area there for yourself. That's actually so prominent that it has its own catalog number, an NGC number. That stands for, I think it's New General Catalog of 604. So very, very prominent region. And you can see, let me go back to my other program so that I can kind of highlight these. Let me get rid of those blue bars here for you. There we go. Bring that back up maybe and remove it. Okay, there we go. You got a couple of more, not quite as prominent, but there's, you know, we got one here. Let's see what happened here. Move this over. That box got moved. We've got one right here just to the south. I'm not sure why that's not moving around on me like that. Well, anyway, you do have a couple of other visible hydrogen 2 locations within the galaxy. It's those red areas that are very, very prominent. Hopefully it's coming through on the stream pretty well. And interestingly enough, you also have some bluish regions, which would represent younger star activity. The red would be more of, I think, an older hydrogen region, and blue would represent more younger star activity being created in Messier 33. So that is our view here for M33 tonight. We got any other, we got some questions, or if we're ready for the next person, that was my spiel.
All right, well, thank you very much, John. It doesn't look like we have any questions at the moment, but you know, we may get some at the very end there. So with that, thank you again. That was a really cool view of M33. So we're gonna head back over to Theo Wellington up in just a little bit north of Nashville. And instead of looking at a galaxy this time, we're going to look at a single object that resides within our own galaxy. Well, actually, hold on 1 second, Theo, if you wouldn't mind. We actually do have a question. So John, why do younger stars look blue and older stars look red?
Now, you all told me that there would not be a test on this broadcast. Let's see, there's something called the HR diagram, Hertzl-Russell. Is that if one of the other amateurs or one of the other professionals out there know? But basically, a blue star is younger and hotter than the older red star. It's younger in its life period, basically. So in the red stars, they've kind of, going through, they're older, they've kind of burned through their hydrogen and they're burning other heavier materials now, which in turn cools them down more so. So that's why they're a different color than, say, the blue stars, which are hotter.
And I'll just add to that. So to be a blue star, you have to be a very massive star. And so very massive stars get very hot, which gives them their blue color. And the more massive a star is, the shorter it lives. So some of the most massive stars may live less than 1 million years, whereas a star like our sun will live about 10 billion years. And then these little bitty red dwarf stars, they may live as much as about 1 trillion years. And so these very hot, massive stars, as John was saying, when they begin to evolve and they start fusing other elements within them, they start swelling up and cooling off. And so the only blue stars are really these very large, massive stars. And so those stars are not going to live for, again, a very long time. So we know that if a star is very blue, it's not been around for very long. So we could still basically consider it young, whereas some of the very oldest stars, or even some of the older stars, are going to be very red in color. So just a little addition to that. All right, so thank you for that, John. And so now we're going to go back up to Thea Wellington. And as I mentioned before, she's going to be checking out something that resides within our own galaxy instead of looking at another galaxy.
All right, so we're going to be looking at an object that a lot of people are familiar with from Hubble images. It's called the Cat's Eye Nebula. And we've looked at some of these in the past. It's artistically, you would say it's the death shroud of a sun-like star. When sun-like stars evolve, like we were talking about, they get to a phase where they're kind of blowing off layers of their atmosphere. And then later in their life, when they just don't have anything else to fuse, they shrink down to a white dwarf. They can't do fusion anymore, but when you shrink, you get hot too. So they give off a lot of ultraviolet radiation, which lights up these shells that were previously expelled. And then depending on the exact geometry of these shells or the angle that we're seeing them at, they're all unique and different and fun. So it's kind of interesting. They're very beautiful objects. They're very short-lived because they only are lit for as long as that white dwarf has enough energy to do that, which is maybe on the order of a few tens of thousands of years. So they're beautiful and ephemeral as well. So let's see, I'm going to go to, so let's see, I'm going to share what you can see. All right, there we go. Share that guy. So that's what the Hubble sees. And that's kind of a pretty image. I mean, it's got lots of detail, so you can see that there were lots of cool things going on at some point in that star's lifetime. Let's see if I have to go over here. Hang on. Click this, click down. There we go. That's a combination of Hubble imagery with X-ray imagery. So things that are hot and shining in the ultraviolet, they also a lot of times are good for X-rays. So that's combined with Chandra X-ray data as well. And so it's very, very cool. And if you really soak it, so that inner part there is what we've been looking at, but there is an extended outer shell that we really have trouble. That's a super long exposure to get that. So that's not what we usually see. So entertainingly enough, this is often called the Countdown Nebula because its NGC number is 6543. So it's easy to remember too. That new general catalog, by the way, new, again, astronomers have funny ideas about stuff. It was new in 1888. So, but you know, astronomy's been going on for thousands of years. So let's see if we can share the view of what it actually looks like. Let's see that screen. Come on. Get my mouse tamed down here. Here we go. Share. All right. All right, hopefully you guys can see that. So that cute little bluish and reddish thing, that's that Cat's Eye Nebula. And that's actually not too bad. We were pretty happy with this tonight. It's not very large. And those are actually only 2-second exposures. So if your eye was at the eyepiece, you would see this. You know, it would just be this cute little faint bluish thing. And to do this, to get this view, we're using a kind of overlarge telescope. The last object I did, the Andromeda Galaxy, I actually needed a wide field of view because it's so big. And so for that, I had a refractor that has a fairly short focal length. When you want to look at something that's kind of tiny, you want something with a really long focal length. So maybe we can get this in the field of view, or I can get some pictures later, but we're using a 20-inch Dobsonian telescope. So it's simple in design, but it's kind of large. But it's a lot of fun, and we do bring it to star parties when we get the chance. So this is our view tonight of the Cat's Eye Nebula. And, you know, maybe it does look a bit like a cat's eye here. You can kind of make that out a little bit. So that's kind of fun. But it's, like I said, it's a planetary nebula. They called them planetary nebulas because they're kind of sort of round and they reminded somebody of planets. So this is one of those rare things, I think, in astronomy that just has an awful, terrible name because there's nothing like about them that's a planet. But they're called planetary nebulae, mostly for their shape. So there's only a few things like that. I think most things we named pretty well, you know. Place where there's no light coming out, looks like a hole and it's a black hole. Spot on the sun, it's a sunspot. So most stuff is well named, but planetary nebulae, not so much. But this was our first time trying out this telescope with this camera, so we were happy just to make it work, actually. So anybody have any fun questions about these? This is, again, one of the brighter ones, so it's a good object for a backyard telescope.
That's right.
Actually, Theo, would you mind talking about what you see as the very bright spot right in the center of that?
That's a good question. Hopefully that's the central star, which again is a white dwarf. I'm not sure how well focused we are. Let's see. Yeah, that's probably it. So white dwarfs are stars at the very end of their lives, and they're small, well, not relatively small, but stars like the sun end up like this. They lose mass in their red giant stage, casting off all these layers that are now beautifully illuminated. And then once they finally can't fuse things anymore, they just start shrinking. They can't hold themselves up anymore. They're not making energy. So they just generally shrink down. It takes a long, long, long time to cool off a star, though. So, you know, it'll get dimmer gradually over time, but it takes billions and billions and billions of years to completely cool off a white dwarf. I mean, eventually it'll go dark, but that will take a very long time. So, but they're nice, pretty little stars. Now, sometimes they're by themselves, like our sun is. And so they just get to live their lives and die. Sometimes, though, they're companions to other stars. And if they go through their evolution first, they're a little white dwarf sitting there just trying to cool off, but the other star now swells up in its red giant stage, and they're close enough so that the other guy starts dumping matter onto the white dwarf. That's not stable. So eventually a huge case of indigestion occurs, and the stuff that's dumped on the white dwarf flashes off, and sometimes the whole thing goes kaboom at that point. You have too much mass, things start happening, and you get a giant nova, you get a supernova. And because that happens for white dwarfs at a particular mass, they're all kind of the same exact brightness when they do that. So that's been another one of our fun distance candles to use in the universe. When we see a white dwarf supernova, we know that about how far away it is by how bright we're seeing it. So that's kind of a fun fact too. They've been used to scale the universe, and it's studying these kinds of supernovae because they're thought of as standard candles, that they have been used to show that the universe's expansion is not steady or not slowing down, but actually appears to be accelerating. So they're kind of boring. You know, you think of a white dwarf just sitting there cooling off as being kind of boring, but actually they're kind of interesting, and we've used them in a fun way. there. Nebulae at this phase are just really pretty things to look at.
All right, well, thank you very much, Theo. I just wanted to add to it that that little white dwarf that we're seeing in there, it looks large, and that nebula is probably about a light year across. And so it looks like that white dwarf would actually be humongous. But light, when it goes through a telescope, doesn't matter what kind of telescope you have, just because the properties of light itself, light spreads out. And so the actual physical size of that white dwarf is many, many times smaller than a single pixel in that camera.
Yep.
But because of the light spreading that goes on, it's called the point spread function, if you want the technical term for that. That makes it look bigger. But what we're actually seeing is an object that's about maybe half as massive as the sun, but it's physically only about the diameter of the Earth. So it's very small, it's very hot, but that makes it very faint. But I do want to say that this is, you can actually see that white dwarf in this nebula. I remember the first time I saw this nebula through a moderate-sized telescope, and the first thing that struck me was actually getting to see that white dwarf. When you look at some of these other planetary nebula, like the Ring Nebula, which we've seen before, or the Dumbbell Nebula, those are planetary nebulae as well, but you can't really see the white dwarf except for those long exposure images. So,
Yep.
and
Is about over 3,300 light years out too, so it's not super close, but yeah, it's nice and bright.
but still easily within our galaxy.
Yes.
There was one other question: how do you locate the Cat's Eye Nebula? Which constellation is it in?
It's in Draco, the Dragon, which is a cool little constellation that winds between the Big and Little Dippers. This is sort of towards the end of the tail, if you like. So it's a little higher than the Little Dipper at the moment. How do you locate it? Well, it depends. If you've got a telescope that's got the cute little, hey, I want to go to NGC 6543, go, then it goes. Otherwise, what you do is you get out a great program like what John's been showing you, Stellarium, which is wonderful, and you start star hopping. So you find a pattern of bright stars, and then maybe using binoculars, you start, okay, there's that pattern, then I move to this one and this one and this one, and you can actually get to objects like this and be really tiny and faint in binoculars. But that's how you can do things in a telescope, even without the fancy computer functions. And it's surprising how easily you can make little charts that basically, okay, I'm going to move this far in this direction to this star, and you can hop along and then find these things. So
Okay.
it's a challenge, and it's a fun way to really learn the sky and get good with your instrument to do that also. I see as well, what camera are you using? This is a cute little color camera. It's usually used as a guide scope. It has a tiny, tiny little chip, which is what made this a challenge. It's called a QHY, I think the 52C, and it's just a can, because it's really just a little cylinder with a chip, because we don't need the whole rest of a camera for doing this kind of stuff. We just need the chip. So that's literally the camera chip in a can, and then it's, got an out to go to the computer. So it's, this is a relatively inexpensive camera. Like I said, usually I don't use it for photography per se. It doesn't have that many pixels, but it's good for a guide scope. And what a guide scope does for you is you can tell it, say one of the faint stars down there, you'd say, hey, keep the telescope on that star in that place. And it will then work through the mount to issue commands to say, okay, I'm going to hold it there. And that lets you take long exposures where nobody moves. You don't get star trailing and things like that. So it's a nice little camera, and it's doing a pretty decent job for us tonight.
All right, well, thank you so much, Theo. All righty, so I guess the program goes back to me for just a moment. So we've got another object we're going to check out. So we've been looking at a lot of deep sky objects like galaxies and some star clusters, and then some planetary nebula, as Theo just showed us. But we're going to go back into our solar system and check out another object which we haven't actually seen before on our program. So let me do a quick screen share. And there we go. So this image doesn't look quite as colorful as a lot of the images that we've been seeing of galaxies and the planetary nebulae and the clusters. But personally, I think this is a really neat image. So you'll see up here in the top left of my screen that we've got about a 3-second exposure going. And you can definitely tell that there is a little bit of blue color to this. So this is not Uranus, but this is actually the planet Neptune. So Neptune is about 30 times farther out from the sun than the Earth is. But if you have even a small telescope, you can actually spot this. It's a little bit too faint to be seen just by the eye. If you have a good pair of binoculars and you know where to look, especially if you have a good star map, you could actually pick this out. So Neptune wasn't known since antiquity like the planets Mercury, Venus, Mars, Jupiter, and Saturn, because all of those planets could actually be seen naked eye. Uranus was a little bit too dim to be seen by eye, and because it's right at the limit of naked eye visibility, but because it moves so slowly through the stars, or among the background stars, we don't really notice it moving every year. So it wasn't discovered until about early part of the 1800s. Neptune was actually first figured out to likely exist because of mathematics. So as I mentioned before, Johannes Kepler had devised 3 laws of planetary motion, and then Sir Isaac Newton expanded upon that to formulate his universal law of gravitation, which we could then use to really accurately predict how planets would move and where they should be at certain times. And so after many years of observing Uranus, about 30 to 40 years of observing Uranus, astronomers noted that Uranus wasn't quite following where it should be. And so it was thought that maybe there was another planet whose gravity was actually pulling on Uranus and causing its apparent position to deviate just a little bit from what was predicted. And so two astronomers had independently had predicted where this planet ought to be before it was actually found through a telescope, but it was actually found where it was predicted to be. So that was back in 1846. In 2011, we actually just celebrated Neptune's birthday, which is the time since its discovery back in 1846, and it takes 165 years to orbit the sun. It had made exactly 1 orbit since its discovery. So it'll be another about 65, about another 156 years before we have another one of Neptune's birthdays. But anyway, in a moderate-sized telescope, you can definitely tell that this does have a little ball structure. Now, as we'll see, Neptune is bigger than the Earth. In fact, all of the gas giants and the ice giants are larger than the Earth in both diameter and mass. Now, before we leave our live view for me to show you a couple of slides, I want to bring up the exposure just a little bit. So let me rephrase that. I'm going to bring up the gain. So I'm going to basically amplify my signal in the program to try to make the fainter things brighter. So I'm going to bring it up quite a bit. And then boom, right there, about 5 o'clock position of Neptune, we have this other little dot there. And you'll notice that as the atmosphere is shifting and we get our new exposure in, Neptune looks like it's bouncing around a little bit as well. And its little companion is doing the same thing. That is actually its largest moon, Triton. So Neptune, as far as we know, has at least 14 moons. It will likely be that other moons are discovered, especially if we send other missions out to visit Neptune. But this is by far its largest moon, just a little bit smaller than our own moon. And Triton, not to be confused with Saturn's Titan, is a pretty interesting object, and I'll show you some images of that in just a moment. Now, likely next month or the month after that, when Uranus gets up higher, we'll take a look at Uranus, and you'll see that it looks a little bit larger in our view because it's closer to us than what Neptune is. So let me pull up just a couple of slides here and give you just a quick lowdown about Neptune. Actually, let me start my slideshow. Give me 1 second. slide. All right. And so Theo, you're not the only one that talks to themselves while they do this. All right, so now we should be able to see Neptune. In fact, I think I am one slide too far. All right, can everybody see Neptune and the Earth there? All right, cool, thank you. So here is a scale comparison of our Earth and Moon versus Triton and Neptune. So Earth is about 4 times smaller in diameter. Neptune is about 17 times as massive as the Earth. But as you can see, our moon is about 4 times smaller than our Earth, and Triton is just a little bit behind that. So we've only visited Neptune 1 time, and that was back in 1989 when Voyager 2 did a flyby of the planet. So it didn't go into orbit around Neptune, stay there for a little while, taking images and really studying Neptune, its moons, and as we'll see, its rings. It actually just passed right on by, but as it was passing by, it was quickly snapping images, taking as much data as it possibly could. And so we learned a lot about Neptune and its moons and its rings during that flyby. So hopefully in the coming years, we will have another mission that will head out to the outer solar system to visit Uranus and Neptune, both for a second time. So as it turns out, the reason that we visited Neptune in the first place was that back in the late 70s, when the Voyager missions were being constructed, it turns out that the planets Jupiter, Saturn, Uranus, and Neptune were coming into a good position within our solar system, so that if we were to send one of the Voyager probes to Jupiter, we could do a flyby of Jupiter and use Jupiter's gravity to help send us onto Saturn. And then once we got to Saturn, we could use Saturn to then help send us on to Neptune, or excuse me, to Uranus. And then we do the same thing. Once we get to Uranus, we head on to Neptune. So Pluto wasn't in that line as well. Otherwise, we would hopefully would have visited Pluto back then. So that alignment doesn't occur very often. It's only once about every 175 years, if I remember correctly. But anyway, we did get to visit Neptune, and we got some really great views of it. So Neptune has some interesting features on it, or had some interesting features anyway. So these are individual images taken by Voyager 2 mission as it was going by Neptune. And so those were combined into a movie. And so you see that there's one very prominent feature that went right through here. And unfortunately, my movie is having a little bit of an issue. But that dark region that you're seeing right there, that is known as Neptune's Great Dark Spot. So if you think back to Jupiter, Jupiter had that massive storm that we call the Great Red Spot, which has been observed for at least a few hundred years. The Great Dark Spot on Neptune looks like that was a much more short-lived storm. First time we saw it was when Voyager 2 passed by. And then when the Hubble Space Telescope was launched back in 1990 and the first observations of Neptune were made, it was found that that Great Dark Spot had disappeared. But then in subsequent years, other versions of the Great Dark Spot had emerged. So Neptune has a number of moons. Has 14 of them as far as we know, or at least 14, I should say. As you can see in our view here, there was one discovered back in 2004. This wasn't from a flyby of the planet, but actually from a long exposure image from a telescope here at the Earth. But you can see how some of these moons are in orbit around Neptune, and so Neptune would rotate. If we viewed it from above, it would rotate counterclockwise, just like all the other planets do. It would orbit counterclockwise around the sun, again, if viewed from above. And the moons that are in orbit around Neptune all do the same thing, except for that one interesting moon that we just highlighted earlier. So Triton, which is the largest of those 14 known moons, it is in what we call a retrograde orbit. So it doesn't orbit in the same direction around Neptune as the rest of the moons, which is the same direction that Neptune rotates. What we call the regular moons of Neptune They orbit in the same direction. They have pretty circular orbits around Neptune, and they orbit basically around the equator, which suggests that they likely formed around Neptune. But Triton, it goes in the opposite direction. It's in what we call a retrograde orbit. Its orbit is also inclined as well. So it likely did not form around Neptune. In fact, it resembles what is known as a Kuiper belt object. Pluto is the most famous of the Kuiper belt objects. So this was likely one of those leftover remnants of our solar system's formation that encountered Neptune and got pulled into orbit by Neptune's gravity. So this is a composite movie of images from the Voyager 2 flyby. So there's a nice starry background, just kind of giving a kind of what a view might be if you were out in that part of the solar system watching all of this go by. So these are actual views of Triton as it was being imaged by Voyager 2. Again, unfortunately, my movie's having a little bit of an issue here, so I'm going to pause it. But what you're going to notice is that there's a lot of interesting terrain features. In fact, this region right up here is very, very smooth, which indicates it's very young because if it's a very old surface, then it's going to, over time, have been battered by craters. This part of the surface is often likened to having the texture of a cantaloupe. But this very smooth surface suggests that Triton was actually geologically active. It's not just this frozen ball of rock and ice, but it may have had some internal heat source that has helped keep activity going on within it that has shaped the outer surface features. All right, I'm going to go ahead and skip over to my next slide since this is apparently having some issues. Give me 1 second here. As Voyager 2 flew by, it also noticed some of the geologic activity that was going on. Now, this is a very small crop of a low resolution picture of the surface of Triton, just a very small area. But Triton was found to have about at least 4 active geysers on its surface. As that material was spewed up into the sky of Neptune and then fell back, it was actually casting a shadow that we can see here. Let's see. And then finally, Neptune, like all of the gas giant planets, and which Uranus and Neptune are known as the ice giants because they are much farther out than Uranus and Neptune, and they do have lots more ices in their atmospheres. But all of these planets do have ring systems. They're just not as magnificent as Saturn's rings we saw earlier tonight. The rings were actually are known before Voyager 2 got there. And Neptune was kind of interesting because its rings apparently had these ring arcs. And you can see in the right side view here that this ring has this high concentration of material in here. And so astronomers had detected the presence of these arcs before Voyager 2 got there by observing stars that were being occulted by these rings. So as Neptune and its ring systems are moving around the sun, occasionally Neptune or its rings, or both, will pass in front of a background star. And so if astronomers watch that star very, very carefully, and they monitor the brightness very, very precisely, they can measure little dips in the brightness of a star that as a result of, say, a ring passing over, that star momentarily dimming in a little bit, or it'll wink out completely when a planet passes in front of it. So what was found was that as these rings passed over one of these background stars, we saw a certain amount of dip in the brightness. But then when the other side of the rings passed over, we didn't see that same dip. It was a little bit different, which suggested that the rings weren't uniform. And it really wasn't well understood how that could be because the rings should really even themselves out. But it looks now like it may actually be due to resonances with some of the moons that orbit very close to these rings. In fact, some of the recent observations from the Hubble Space Telescope have shown that some of these ring arcs look like they're actually dissipating and may be gone within a few decades. So Again, we haven't visited Neptune in a while, but still, it's you can see it in a telescope. You can see Uranus even better. You're not going to be able to see the rings, though. They are just way too thin, way too dark. In fact, they're much darker. And the material that they're made of is much darker than the icy material that we see in Saturn's rings, because there's a lot more organic compounds in those rings. And that organic compounds, they tend to darken over time because of ultraviolet radiation from the sun. So they're very, very dark. These are very overexposed images, as you can see, of the left and right side of the ring system there. But that was required in order to see these very, very dark rings. So if you get a chance, please do try to check out Neptune. You know, if you don't find it at first, just keep trying, but look for that blue color. It should be pretty prominent. And you'll notice that it is definitely a tiny little ball as compared to those background stars. So, let's see here. Let's see if we've got any questions before we move on here. So why do the moons tend towards rotation in a similar plane? So this actually goes the reason that we have these motions is a result of how we think this whole solar system formed out of originally a very large cloud of gas and dust. And so we see examples of solar systems in the process of forming elsewhere in our galaxy. But basically, as gravity tries to collapse down a rotating cloud of gas and dust, centrifugal force actually prevents the collapse from the side. So if the cloud is rotating, say, this way, the centripetal force actually halts eventually the collapse this way, but it can't halt the collapse from gravity this way. And so that material in our cloud then collapses to form a disk. And in that disk, you get material starting to stick together and run into other pieces of material. And eventually you get these blobs of material that start growing larger and larger. And eventually, once they get to, say, kilometer size, they have enough gravity that they can start very gradually pulling other material in. And it's basically a snowball effect. As more material is added onto an object, its gravity increases, which allows it to pull even more material in. And so these objects then start growing through gravity. But because we essentially had the same mechanism around a forming planet, where we have a material in orbit around the forming planet that starts sticking together to form the moons, all of these objects basically form within that disk. And that's why we see all the planets basically orbiting in roughly the same plane around in our solar system. And so these regular moons, or what we think are, when we say regular, we mean moons that actually formed around these planets. We think that they're regular because we see them in basically the equatorial plane of that planet, which is right smack dab in the center of that disk out of which the planets and those moons formed. And so like Triton, we think that it's one of these objects that got too close to Neptune and got into orbit around it because it's got such a drastically different orbit from all of those other moons that it really couldn't have formed around Neptune and had that type of orbit. Because remember, it's going backwards of what the other planets are, or what the other moons are moving, and it's not orbiting in that same plane. It's actually inclined quite a bit. So, but yeah, the whole reason they're orbiting in that same plane is because of the formation mechanism. So when we look at other stars that are forming in these large clouds, we can see disks of material around these stars. And in fact, in some of these disks, we've even detected gaps, which might be due to the presence of planets forming and basically clearing out areas within that disk. So there was another question, why is a storm centralized in such an intense focused area? So this is basically, so the great dark spot or the great red spot, these are due to convection within the atmosphere, just like hurricanes on the Earth are formed as a result of convection in the atmosphere and also the rotation of our planet. And so as warmer material from below rises up because it's less dense, we get this nice column of air forming. And then as this air is coming up, we've got different zones within the atmosphere at different latitudes that are moving in different directions. And they're moving in different directions because, as a result of the rotation of the planet itself. So you basically get this column of air rising up in between, let's say, a band of air that's moving this way and a band of air that's moving this way. And so it's kind of like it's spiraling in between there. We see that with the Great Red Spot on Jupiter. And so those bands tend to help keep these storms somewhat kind of condensed down, if you will. Let's see. So do we know what Neptune's rings are composed of? Is it ice like Saturn? So they do have ices, but they've also got a lot of other compounds in them. Like I mentioned before, organic compounds, which are compounds that contain carbon. So as these organic compounds are exposed to ultraviolet radiation, they tend to want to break apart, which tends to free the carbon within those compounds. And if you've ever looked at a lump of carbon, it's like coal. Okay, so I mean, these rings are incredibly dark, and so they've really been lightened in this image. So why don't the inner planets have rings? One of the issues is their small mass, and so you've got something known as a Roche limit. That is the limit to which a moon or a very large object, so not like a space station, but something like a moon. The Roche limit is the closest in that an object can, like a moon, can get to a planet before the planet's gravity actually ends up shredding it. And so that Roche limit actually scales with the planet. So the rings of Saturn, for example, all of those particles are within that Roche limit, which is why we think that maybe a moon could have gotten too close into one of those to Saturn and got torn apart to form those rings. And so these, also in order to have a magnificent ring system, you've really got to have a fairly large body, or not tremendously large, but it helps to have a larger body. So it's basically just a combination of effects that are due to the low mass of the planets. So with that, I think I may have taken a little bit too much time, so I apologize. So let me stop my screen share. And I think that we are going to head over to now to Adam to finish up our evening and talk a little bit about Mars. So while he's doing that, I'm going to try to get another view in our telescope. So Adam, if you wouldn't mind taking it away.
All right, thank you very much. Well, I'll have to say we've had some excellent questions from our audience. It really enhances the program, and it makes it more worthwhile and more live. And that's what it's all about. Getting, educating, teaching, sharing the night sky. So I was going to be talking about Mars, and if you have been following the news a little bit, you might have heard that Mars is at opposition right now. And what that means is that Mars is opposite the sky of the sun. But think about this. What it also means is that when you look at our solar system from above, as an example, let's see, from above, you're going to be looking down at the orbits of each of the planets. So Earth is the third planet from the sun. Mars is the fourth planet from the sun. Because Earth is closer to the sun, it goes around the sun faster in its orbit. Earth takes 1 year to go around once. Mars is a little over 2 years. So what's going to happen is about every 2 years or so, there's a point in which Earth is kind of overtaking Mars in our two respective orbits. And think of them as little race tracks, like the little slot cars. They can't leave that little slot. And so the inner car will go faster on the inner curve than the outer car or outer slot car. And so Earth is overtaking. So where we are is at that point where we are overtaking Mars. And Mars is also what is called perihelion. And that means that it is at its closest position in its orbit, because its orbit is oval shaped, egg shaped, all orbits are oval shaped. There's no such thing as a perfectly circular orbit anywhere. And so there's a point where a planet going around the sun, a moon going around a planet, it goes on like that, can be closer to what it's orbiting, and another time on the other side of its orbit that's farther away. So we actually have both of those things to our advantage. Also, Mars, if you actually look at it now or next 30 minutes, you're going to see it's really high up. And so it's actually getting above, that thick atmosphere that you see down at the horizon. And the higher an object is in the sky, the less of the atmosphere it's looking through. Perfect situation is zenith, which is then 1 atmosphere. Anything lower than zenith, the point directly over your head, you're looking through a thicker and thicker amount of atmosphere. And so that will dim the image. It also means that it's more turbulent air that you're looking through and greater chance of turbulent air. So that said, right now, we're actually just about a number of days past opposition, and we have another month or so for excellent viewing where we're going to see Mars look larger than normal. Now, I want to show you some quick images. I took this particular image about a week or two ago, about 2 weeks ago. You're going to see it small. You're going to see some dark areas on there. Anybody who's familiar with Mars will notice that little kind of triangular little pointy bit that is Syrtis Major. And very teeny tiny on the very tippy top, tiny little white circle, that is the southern polar cap of Mars. This is how Mars is tonight. You're not going to, no, this is not a photograph that I took, but it's at this time. I'm only 4 minutes off. You're going to see kind of a dark area kind of crossing the middle of the planet. If we were able to, we would see a little polar cap and also Olympus Mons and Tharsis Bulge, which are huge volcanoes on Mars. No, we're not going to see that. I just wanted to show you that. Then also what Billy's going to try to show you are the moons, the 2 moons of Mars, Phobos and Deimos. Phobos is very close to Mars right now. Deimos is at a distance. He did show us a photo that he took the other day, so he should be able to show that. I also want to show you, very quickly, this image. This kind of tells the story, and then I'm going to show you what I am seeing of Mars. But I wanted to kind of give you a basis of understanding. Notice this image. You're going to see the moon, our moon, 33 arc minutes wide in that image, or 1980 arc seconds. Remember the double cluster I showed you earlier? That was about 30 arc minutes together for both clusters as far as their size, 30 arc minutes. The moon is about that same size. Notice the 2 images of Mars above the moon in this picture. It is just an illustration. It is not a photograph, but the bigger image is how we see it now. As you can see, it was a week ago. And you see how tiny Mars is. And then below it, farthest from the Earth, 3.5 arc seconds. It's this micro little dot. That's why astronomers, both professional and amateur, get all excited about opposition, because it's so much larger looking than it normally is, even though it is smaller looking than many of the craters on the moon as far as how we see it. So it's still pretty tiny, but it's better. Okay, here's the live image of Mars. I apologize. The atmosphere is not being kind to me. You're going to notice the disk of Mars. You're going to see kind of that dark area going across Mars near the middle there, slightly above middle. I hope you do see that. That dark area is basalt. It is a rock that is formed from lava flows. It is the same basaltic type rock we see on Earth, especially in the ocean floors when our tectonic plates spread apart and magma from below upwells and cools off and hardens. That is basalt rock. Also on the moon, basalt, that's the dark maria, the seas, put quotes around that, those dark, large areas. That's lava flows, that's basalt. Same on Mars. So a similar type of geology in the sense of the same rock is seen in many places. The red color, of course, it's not red, it's kind of orangish. Well, the surface of Mars is kind of a desert with exposed basaltic rock or sand-covered areas, but that color is from iron oxide, rust. Mars is a rusty world. The reason the name for Mars is named for the god of war, because it looked in the sky like a drop of blood hanging there in the sky. Of course, that's not what it really is. It's rust. And because of the iron, bits of iron in the sand, or we'll call it soil, but it's not living soil, has oxidized. That means it was exposed to oxygen. Where do we find that? Water. Water once covered a lot of Mars. It has evaporated away over time. Its atmosphere is so thin that it can't hold an atmosphere, nor even an ocean. And so all the water and everything is just evaporated into space. There's a little bit of water in the atmosphere. You'll see some occasional white clouds. You will also see in the polar caps frozen water. And down below the surface in the permafrost of Mars is frozen water. And so if we're able to extract that water with remote drilling type devices, you can get drinking water. You can split the water into hydrogen and oxygen, then compress it. You've got fuel. That's what the space shuttle ran on, was liquid oxygen and liquid hydrogen. And so a lot of great things from that. And that means we don't have to carry a whole bunch of water if we want to go to Mars and send people. Notice the dark areas. You can, every once in a while, you're going to see some features there. On the very top, I'm seeing the polar cap, just a little flash of white on the very tippy top. I know Billy will have a better view of Mars than I do here, but I wanted to show you what I'm seeing. But you can see how it's just dancing around. The seeing is not good.
Hey, Adam, sorry to interrupt, but
No.
if you want me to switch over to my view, our seeing is a little bit better here.
I bet it is. How will we do this? I see a question. Are you going to manually just take the image and do yours?
I mean, if you just want to continue talking, I'll show my view, and then when you're ready
Excellent.
to try to pull up one of the moons, just let me know.
Okay, so bring up your image. Yeah, that's better. Yeah, you can see that elongated dark area, which you kind of see on mine. But what Billy is showing is more features, especially below that dark area. So you're going to get these slight variations. Excuse me. So they have a much larger telescope and better seeing where they are. Mine is just taunting me. It's dancing around. So the question, does Mars get to zenith in cooler weather? That's a great question. What's actually happening is, all right. Do you remember how Billy talked about Neptune and the moons of Neptune being in that plane and along the equator? And we also saw how with Saturn, we saw the rings system of Saturn on the equator. Well, take those same dynamics and apply it to the solar system. The planets orbit the sun in a plane, and it's at the same plane of the sun's rotation because they all formed at the same time. And so we will see Mars as well as the other planets along what we call the ecliptic, which is the apparent path the sun makes across the sky. This time of year, the ecliptic gets very high in our sky at night. In the summertime, the ecliptic is very low. Because of where Mars is in its orbit, we're seeing it at this time of year. Therefore, we're seeing it high up. So it actually has nothing to do with the weather, but where it is in the solar system orbital plane. And then how do you get it to run on liquid oxygen? Okay. The space shuttle, you saw the big external tank. Half of it, or 2/3, I can't remember the ratio. But anyway, let's say half of that was liquid oxygen and the other half was liquid hydrogen. When you expose those two to each other, when you mix those two, it is highly explosive. That's rocket fuel, and that's what the space shuttle uses. And that's what goes through the engines of the space shuttle. It'll be the same thing that's going through the engines of the SLS when it's finally finished, and we're actually able, and other rockets. The solid rocket boosters on the side of the space shuttle, that is a solid rocket fuel. And it's like a Roman candle. Once you light those suckers, you can't turn them off. But you can control liquid oxygen and hydrogen and how they mix and how much they go through the engine and throttle down and all those wonderful things. And it just takes the ability to compress it to get it cold. So I hope I've answered that question well. Billy, did you want to add anything, or?
I was just going to bring up our exposure here and see if we can get something here. The seeing is still not very good. Let me bring up our exposure a bit more and bring our gain down. Yeah,
Is
right.
that a lot? Yeah.
So right there, yeah, it's really hard to see, and he's kind of going in and out because our seeing is not
Can
that
you increase the exposure because it was visible then?
a little bit better there.
There you go. Yeah.
That one is Deimos.
Yes.
Now Phobos
Away.
is actually down here, but right now it's a bit too close to Mars for me to be able to pull it out. I've been playing with the settings and I can't get a happy compromise, but at least we got the one moon there. But I'll bring up the other screen right quick. So this was an overlay view that I got the other night. So I've taken the overexposed Mars and overlaid a regular exposure, but you can see right there, there's Phobos and there's Deimos there. Now my view is a little bit rotated from what it was the other night, and that's why the moon, this moon down here is not way up here now. But, and I guess just one other thing is, here's what they actually look like. So these guys are likely asteroids. They have a lot of characteristics of asteroids, but they do orbit around the equator of Mars. They are in pretty circular orbits, but they are very likely captured asteroids. But the jury is still kind of out on that. And one thing I forgot to put in here, but I'd encourage you all to look up, is the rovers on Mars have been able to take a picture of the sun as as actually both of these moons have passed over the sun and created an eclipse. So it doesn't block out the sun like we have here on the Earth, but you can see this little dark feature going across the sun there, which is pretty neat. And one final thing, Phobos, which is the closest in of those two, it actually orbits the planet faster than what the planet rotates. And so if you were standing on Mars watching, you would actually see Phobos rise up over in the west and then gradually move across the sky and set over in the east, which is kind of weird how, especially comparing it to what we see here on the Earth. But that's the only thing that I had.
Oh, okay. Yeah, I mean, I would say they're probably captured asteroids. And they're really tiny. I can't remember the exact size, something like 50 miles or something.
Actually, I got it right here. Phobos, our largest one, at maximum is 26 kilometers. So it's about 15 miles wide at its maximum. Yeah, pretty dinky.
Yeah, they're very tiny. Yeah, they're just little itty bitty guys right there. Just I don't see any extra questions, but that one image, yes, Deimos, the one that was live, was at the 2 o'clock position. Mm-hmm. And it's one of those things. Right now, if you were able to have steady skies, I mean, I'm just thrilled. I can see a nice round disk, and I can see general features on Mars. I just wish it was steadier. But another bane of the astronomer is global dust storms. And Billy, did you show a picture like that the other time? I think you're muted.
Yeah,
But
one, if you give me 1 second, I will.
okay, I'll just talk briefly and you can bring it up. These dust storms occur, and because the atmosphere is just so thin, it's 1/100th the amount of the atmosphere here on Earth. So even if it was air, you couldn't breathe much. You couldn't breathe it because there's almost nothing there. But that dust is like a powder. It's almost like baby powder, but it's a different kind of material. But it's that fine, and because of that low atmosphere, that stuff just aerates and it just gets all over the place. And as you can see in this image, it will cover the entire planet. Now, Mars is about half the diameter of the Earth. So it's twice the diameter of the moon, half the diameter of the Earth. But just thinking about one storm system that affects the entire planet is pretty amazing. And you can see what happens to the view. Totally washes out anything that you can see. Right now, there is no dust storm, and so we're still lucky enough to be able to see something. And there's been thought that it's related to increased temperature from the sun as it gets perihelion, and somehow affecting this. I don't know, Billy, if you've heard any other kind of relationships.
A lot of it is thought to be done with or due to the effects on the polar ice caps. So a lot of that CO2. So a lot of the ice that are here are CO2 or carbon dioxide or dry ice, and that sublimates and can kick up winds. So that's all that I can add to that right now.
Okay. Yeah, the polar caps actually change in size. From Mars's summer and winter, depending on the north or the southern pole. It's cold enough that the water ice never melts, but the temperature fluctuation at the poles is enough that the carbon dioxide can freeze or evaporate. It's fluctuating above and below that freezing point for carbon dioxide. And so the caps can actually look different depending on the season, on Mars's season. And okay, do I have better seeing purely due to elevation being in East Tennessee? Well, to answer that question, I'm actually observing from my home. I'm at 3,000 feet. That can be a slight benefit, but I'm in the mountains, and that can make the sky very turbulent. Where Billy is at Vanderbilt near Nashville, it's flat out there with some rolling hills. And so it just kind of depends. Sometimes we have had excellent seeing here, and generally better weather because we're a little higher altitude, and the valley areas will tend to get sucked in with moisture. But out west in the desert is excellent. Also in the ocean where there's just no mountains or nothing, it's water. There's very laminar flow, and you can have excellent seeing. So it kind of depends. You get a front coming through, and that's it. It's going to tear up the atmosphere anyway. It doesn't matter where you are. So it's all kind of a luck of the draw kind of thing. We're all shaking our heads. Yes, we all know about that.
Yep. All right. Well, thank you all so much. So are there any other questions from our audience? It could be about anything that we've spoken about tonight. And while you all are pondering that, I just want to mention something I forgot to mention at the beginning of the show. It was in our preliminary slideshow, but on Dyer's homepage, we've got links to some star charts for that are set to basically for tonight, but you can use them throughout the month and into next month as well. But it highlights where a lot of the objects, actually all of the objects, are that we were talking about tonight. So, download that and check it out. There's two versions, one that doesn't use very much ink at all, so you can print that out if you want to, or a really nice colorful version if you want to just use your computer or your phone. So it does not look like we have any, oh wait, no. Is the smoke from the fires out west affecting your seeing? So I know that we actually saw a fair amount of the smoke come in at times. I think it was about a month ago, and that did, I don't know if I'd say it affected our seeing, but as in the turbulence, but it definitely did hinder some of the light that was coming through. So it made things, I remember looking at Jupiter, we had just gotten some of our new cameras in, and Jupiter and Saturn were noticeably oranger in the views than what, say, we saw tonight. So I don't know about the rest of everybody else, but.
We didn't actually see the smoke here where we live, but because I think it went north of us. We had heard from friends from, the Midwest and like Chicago, and they were seeing tons of smoke. There's a lot of different factors that go into how well you can see something in the sky. The term seeing relates to turbulence. How steady is the sky? Then there's transparency, which is how clear is the sky? So out west, it's really clean air. There's nothing in there. There's no pollen like we have out here. So, their night skies are pitch black. It's like a planetarium theater. It's just, amazing. We're being out in the middle of the ocean. And then it's just what's in the atmosphere. Do you have a bunch of junk in it? We have pollen and stuff. And so that's going to attenuate the view, where it may darken it just because of scattering, but also it's scattering the light. So it's gonna, like Billy said, it would make the image redder. And I had noticed some brownish haze off to the east at sunset. So I'm wondering if we are seeing a little bit of the current fires. And then altitude, if you go to like 10,000, 15,000 feet, way high altitude, you're getting above the Earth's atmosphere. Remember, here, wherever you live, zenith is 1 atmosphere. That's at ground level. 3,000 feet here, like 95%, 98% atmosphere above us. You get to 10,000 feet, 20,000, you're looking through a much smaller fraction of the amount of the atmosphere, and it's almost like being in space, though obviously not. And that's why observatories, big ones, are way up top, giant high mountains. So they're looking through a much smaller amount of the actual Earth's atmosphere. I'll stop talking there.
All right, anything else from any of our other presenters?
It's been a good night. I can smell, I think, smoke from a couple of, we got a campground about a mile away, and it's Saturday night, and I think we've had a few campfires going down there. I was trying to decide if I could smell a skunk or not. I'm just going to pretend I don't know.
Well, hopefully the smell doesn't get stronger and stronger. There was a question, can I ask for links to everyone's astrophotography stuff if it's published somewhere? I would love to see it. Yeah. Let's see, we don't have anything currently for Dyer, but Jeremy or Adam or Theo or John?
What do you think? Can we share our Flickr page? Or I have a Flickr page with some of Merrill's images. Be happy to share that. He's got quite a collection.
Which, by the way, on behalf of everyone, I want to thank Merrill for letting us make use of this observatory virtually. It's very impressive, and thank you so much for that opportunity.
You're welcome.
He's happy to help. I think you still have the biggest gun, though.
Yeah,
Billy. So with a little bit of resentment over here, but we'll get over it.
Well, it's a 24-inch telescope, and somebody's going to get a 26-inch telescope, but ours will still outweigh them. I mean, the telescope itself is about a ton, so
Oh my goodness.
I think we'll hold that title for a little while.
Enjoy it while it lasts.
Yeah, exactly.
Yep.
All right. Well, thank you all again, all of our presenters. This was awesome. And thanks to all the folks behind the scenes, Nathan, Alex, Brian. Couldn't have done it without you. So we'll start looking at what we can do in November. And I know some of you may have questions about, what kind of telescope to buy. So we may be doing some segments on that. And just check out all of the different groups that have been on tonight: the Barnard-Seaford Astronomical Society, the Memphis Astronomical Society, Bays Mountain Park and Planetarium, and Dyer Observatory. I don't think I'm leaving anybody out. But we're going to have stuff posted on there, different resources. So if you have questions about telescopes or anything, you feel free to contact any of us, and we'll be happy to try to answer to the best of our ability. So, all right. Well, thank you all for joining us tonight. We look forward to seeing you all in November. So just check out the Dyer homepage for updates on when our next star party will be. Hope everyone has a great rest of the weekend.